Hello, my name is Kim Stein, and I'm a scientist at the Gatorade Sports Science Institute. In this session, I'm going to discuss carbohydrate types and their absorption related to exercise. To begin, we'll review the importance of carbohydrate ingestion for athletes, learn about carbohydrate structure and how the different types of carbohydrates are classified, and their absorption and oxidation rates. Overall, in most activities, most of the time, carbohydrate is the predominant energy source to fuel muscle contraction, which is why it is so important for athletes to consume adequate carbohydrate in their overall diet and as part of their sport nutrition plan. When consumed before and during exercise, carbohydrate helps maintain a high rate of carbohydrate oxidation for energy, reduces ratings of perceived exertion or how hard the exercise feels, increases endurance capacity, delays the onset of fatigue, and helps to prevent hypoglycemia or low blood sugar. Since carbohydrate intake is so important, in order to decide on the right types of carbs to ingest, we need to take a step back and understand the structure of the various carbohydrates. In chemistry, a carbohydrate is an organic compound made up of carbon, hydrogen, and oxygen atoms. The picture here is of a glucose ring. In nutrition, carbohydrates are a whole class of foods made up of these organic compounds that include sugars, starches, or fibers. Whether an individual carbohydrate is classified as a sugar, starch, or fiber depends on its structure and the number of glucose molecules. A monosaccharide contains one carbohydrate molecule, and a disaccharide two. Mono and disaccharides are known as the simple carbohydrates, or sugars. When three or more carbohydrate molecules are linked together, they form a complex carbohydrate. Depending on the number of molecules and how they are linked together, the complex carbohydrate is a starch or fiber. Regardless, all types of carbohydrates provide the body with 4 calories per gram. The monosaccharides are the one-ring structures, and the 3 monosaccharides are glucose, fructose, and galactose. The disaccharides are the 2 connected monosaccharides. Sucrose is a glucose plus fructose, lactose is glucose plus galactose, and maltose is 2 glucose molecules linked together. The polysaccharides are long chains of glucose molecules linked together. Amylose is a straight chain, amylopectin a branch chain. These are considered the starches. Maltodextrin is an interesting carbohydrate. It is not just one structural molecule, but rather a group of glucose polymers. Each structure has a different number of glucose molecules in the chain. It is produced from potato or cornstarch and is considered a polysaccharide, but in the body behaves as a mono or disaccharide and has the same oxidation rate as glucose and sucrose. Maltodextrin is a common ingredient in sport nutrition products. To summarize, the monosaccharides are glucose, fructose, and galactose. The disaccharides are sucrose, lactose, and maltose, and the polysaccharides are the starches, amylose and amylopectin. Fibers are also polysaccharides. To translate this to what we actually eat, here are a few examples of foods in each category. Fruits are an example of foods containing monosaccharides, although they also contain sucrose and are rich in fiber. Sucrose, a disaccharide, is table sugar. Sugar beets are a rich source of sucrose. Foods like honey and molasses contain a blend of the sugars sucrose, glucose, and fructose. Milk contains the disaccharide lactose. Foods like bread, pasta, and potatoes contain starches. Whole grain varieties contain more fiber. All plant-based foods are good sources of fiber, beans being one example. Athletes should eat a blend of these foods throughout the day as part of a carbohydrate-rich diet. As with all individuals, they should eat adequate fiber and focus on whole grains, fruits, and vegetables. When you eat these carbohydrates, they go to work immediately in the mouth by interacting with oral receptors. When these receptors detect carbohydrate, they activate reward centers in the brain, and simply rinsing the mouth and spitting a carbohydrate solution has been shown in some cases to improve exercise performance. Beginning in the mouth, through the stomach, and in the small intestine, carbohydrate chains are broken down into their one-ring monosaccharides for absorption. The exception is fibers that pass through the intestine. Once digested, the carbohydrate will be absorbed through the glucose and fructose transporters in the small intestine. And once they're absorbed into the body, they can provide energy to the muscle and brain. If the carbohydrate is not needed immediately, the carbohydrates are stored in the muscle and liver as glycogen. In summary, carbohydrates are often classified as simple and complex based on their structures. But this chemical classification doesn't reflect the physiology of the carbohydrate in the body. Rather than simple and complex, the choice of carbohydrate for athletes during exercise should be based on their oxidation rate, which is determined by absorption at the intestine. On this slide, the types of carbohydrate are listed as simple and complex, as we've been discussing, with the mono and disaccharide under simple and starches under complex. But when we group them as fast or slow based on their oxidation rates, you see the list change. Glucose, maltose, sucrose, maltodextrin, and amylopectin are all considered fast carbohydrates since they are rapidly digested and absorbed and are used by the muscle at a rate of 1 gram per minute during exercise. The slow carbohydrates are fructose, galactose, trehalose, isomaltulose, and amylose. These are oxidized at a rate of 0.6 grams per minute. Notice there is a mix of both simple and complex carbohydrates in both the fast and slow categories. The oxidation rate is part of the support for carbohydrate recommendations during exercise. When active for greater than 60 minutes, and the goal is performance, the recommendation is 30 to 60 grams per hour of an easily digestible, quickly oxidized carbohydrate. Following these recommendations and choosing carbohydrates for a fast oxidation rate rather than if they are simple or complex can help result in better performance. Here's one example of measuring oxidation rates of slow and fast carbohydrates from a research study where subjects cycled for 120 minutes at 65% of their maximal workload, rested for 60 minutes, and then cycled again for 30 minutes at 60%. They drank a beverage with an 8% concentration of labeled glucose or galactose at the end of the warm-up and every 15 minutes during the 120-minute ride. Blood and breath samples were collected every 30 minutes. As you see in this graph, oxidation of ingested carbohydrate, called exogenous carbohydrate, was significantly greater for glucose than galactose. This paper was published in 1995, and I use this example since it's a direct comparison of two individual carbohydrates classified as sugars, showing different oxidation rates. Since then, there have been many published studies on the oxidation rate of different combinations of ingested carbohydrates during exercise and the effect on performance. These rates of carbohydrate oxidation are determined by how quickly the carbohydrate is digested and then absorbed into the body. The intestinal wall has a transporter for glucose, called SGLT1, and one for fructose, called GLUT5. Even though fructose is a slowly oxidized carbohydrate, taking advantage of this transporter in combination with glucose helps drive overall carbohydrate oxidation. Think of this as a two-lane toll booth. If only one lane is open, cars can get backed up on one side and not as many cars will get through. If you open the second lane, even if it's slower, more cars will get through. In this way, you are delivering more total carbohydrate to the body and can also help avoid a backup of angry drivers or GI upset. Here's a study looking at the combination of a fast sugar, glucose, versus a combination of slow and fast, or fructose plus glucose, during 120 minutes of cycling at 60% of VO2 max. You can see from this graph total carbohydrate oxidation was significantly greater when fructose was added. The concept of using multiple transportable carbohydrates becomes especially important for prolonged endurance activities. When going more than about 2.5 hours, performance is improved if the athlete can ingest closer to 90 grams per hour. Since the glucose transporter saturates at 60 grams per hour, This can be achieved by using a mixture of glucose and fructose in a ratio of 2:1. This will saturate the SGLT1 glucose transporter and allow up to 30 grams per hour of fructose for oxidation. Of course, we don't eat only straight glucose or fructose. Upon digestion, longer chain carbohydrates are broken into their monosaccharides for absorption. Common carbohydrate sources found in sport nutrition products include glucose, which is often labeled as dextrose, sucrose, maltodextrin, high fructose corn syrup, cane sugar, honey, molasses, agave nectar, and fruit juice concentrate. For all exercise, it can be beneficial to use carbohydrate sources that provide glucose and fructose. As your duration increases, it becomes more important to use products that include fructose to take advantage of the multiple transporters. Almost all of these carbohydrates I've been talking about are considered sugars. So let's talk about sugar for a moment, since sugar often gets a bad rap. Often on social media or in magazine articles, you'll see pieces calling sugar toxic, and it should be avoided at all costs. But in the context of exercise, and specifically athletic performance, it is important to think about the functional benefit of the carbohydrate choice. Many quickly oxidized carbohydrates are sugars, and that's important because the last thing you want is what you eat to be sitting in your stomach when you're on the court, field, or race course. You want it quickly getting to your muscles for energy. That doesn't mean athletes shouldn't be mindful of overall sugar intake. The amount recommended during exercise for performance is rather small, and the quickly oxidized carbohydrates or sugars should be consumed around the exercise occasion. Throughout the day, athletes should focus on nutrient-rich sources regardless of oxidation rate, including fruits, vegetables, whole grains, and legumes. Fiber is also important throughout the day. The guideline for everybody is 25 to 30 grams per day from food. Because people look to avoid sugar, but still want a good-tasting sweet product, artificial sweeteners are often used. There are certainly times when this is appropriate, including during exercise. But for an athlete who needs energy from carbohydrate, it is important they do not mistake the presence of a sweetener and an artificial sweetener for sugar. To summarize the lecture today, the key points to take away are: carbohydrates are the primary fuel for muscle contraction, and consuming carbohydrate during exercise can help improve performance. The chemical classification of simple or complex does not reflect the physiologic response in the body. During exercise, consume mostly fast carbohydrates, those that are quickly oxidized, but also use a slower sugar, like fructose, that can take advantage of the multiple transporters in the intestine to deliver more energy and help avoid GI upset. Thank you for your attention today as we explored carbohydrates and their absorption, which dictates the best choices during exercise. For additional information, all Sports Science Exchange articles referenced in this lecture can be found at gsciweb.org.